Yeah, in the last session, we covered about single degree Paxos. So if you can summarize, so we need consensus when a group of processes are trying to propose a value. Say we have 5 processes, assume, then all are trying to send 5 different values. Then we need to choose one value among them. So that's where we need the consensus between among all the processes to agree with one value. So for that, what we did is, so every server can act as both a proposer and an acceptor. So by using a sequence number, uh, um, so we can block the older proposal numbers, and if the system is already have an accepted value for the higher order proposal, it will pick the accepted value and then it will send across the acceptors. So from that, we can get one accepted value among all the servers by using Paxos consensus algorithm. Yeah, so now let's move to multi-Paxos, how it is working. So prior to that, we have one question yesterday. Someone is asking, why do we need this greater than or equal to, right? So you remember yesterday somebody asking. So this greater than is needed actually because when I referred this Paxos made simple white paper, so they mentioned like some of the acceptors, they may not receive the prepare, but they may receive the accept. So at that time, to combine both the effects, both the step 3 and 6, they added greater than. That makes sense, right? Okay, if you don't have any.
Yeah.
Okay. Now let's move to the multi-Paxos. So for the basic Paxos, right, what we did is the system choose one value for a particular index. Then basic Paxos is done. Whereas when you consider log, right, that log will be having multiple indexes. Say first of all here, right? So 0th index is add, 1 index we stored jump, and index number 2 is stored move. So by using multi Paxos, we take instance of basic Paxos for each index, then we'll get the multi Paxos by using that. So we'll see how it works. So for earlier, for the basic Paxos, we use prepare and accept. So though these two RPCs contain only 2 values, one is the sequence number and another one is a value. But here we need to add the index also, because for each index we need to propose a value and then accept, right? So we need to add the index because multi-Paxos. So for every index we need to run the multi-Paxos for that purpose. So now this example, the client sends one command to server, and now server internally forward that command to the consensus module. Now consensus module will send to the other servers. Then other servers, once they choose a value, the majority, and then it stores to the log. Once it stores in the log, it applies to state machine in a sequence fashion. Say in the log, we have holes in between, say that nobody has chosen any value. So then that time we need to wait, the log index are full. Then only then only in the sequence, we apply the logs to the state machine. Then we send the response to the client. So, okay. So the problem here is for the basic Paxos, we don't have any indexing, right? Just one index only we use. So default is 0. So for multiplex Paxos, we need to understand which log entry we need to use for a client request. Okay. And then multi-Paxos, we had some optimizations they made. So in the single Paxos, right, we have like all the servers can act as both proposers and acceptors. So if everybody trying to propose a value, then we get a lot of conflicts. And to resolve the conflicts, it takes time. Okay. So for the multi-Paxos, what they did is instead they try to choose a leader first. so that only one node in the cluster will always propose the values. It means to say that is only will accept the client request, and everybody else will only act as acceptors. So so from this way we can avoid the conflicts actually. And then we need to ensure the full replication. So once the value is chosen, we need to ensure that all the servers will choose the same value. That is called the full replication. And then we will see how client side implementation will be done while sending the message from client request, how we handle it. And then there's the last one, when the configuration changes. Say for suppose some of the nodes are down servers, we need to replace them. And then the replication, say for suppose the say we have 3 servers right initially, and we're trying to configure 5 servers, then how the configuration change will affect the entire system. So that will go in detail.
So you have only one master in case of multi-Paxos, right? And rest
Right.
of, I mean, it will only propose the value, right?
Right.
So how do you select that master? Like, I mean, it's a random node any or like?
No, there is an algorithm for that leader election. So in the leader election, right, we select one master. Yeah, that I'm going to explain in the further slides.
Okay, so election will be there. So if that fails, then again election will be there to select the new one.
Right. You are right. Yes.
So that will have a latency then, right?
Oh yes,
I mean,
there will be some latency. Yeah. Until the leader is selected, no client request will be served. Yeah.
Okay. Yeah. Sure.
But that is like pretty quicker. Yeah. I mean, we'll see. Oh, yeah. I think you're right. There will be some latency.
Okay. Yeah.
So for choosing the log entries, so when we get a request from the client, so the leader what it has to be, it has to choose the log entry. In which log entry I need to put the client command. Okay. So what we do is, for suppose that there's an example down like server S1. So the cluster containing three servers, I assume S1, S2, S3. So the majority is 2, right? 3 by 2 plus 1. So if you get majority 2, then the value is chosen. So here the steps is we run the basic Paxos to prepare to propose a client command for the index. For that index, the value is already chosen. The value is already accepted. So if somebody accepted, then what we do is we choose a same value and then we continue. If nobody accepted any value for that index we choose for that particular client request, the client command. Let's go to this example. Say in this case, server 3 is down. Okay. So we have only S1, S2 are up. So now S1, if you see the log index, right, it has move, add, compare, and there are 2 holes, and then there's one more command, ret. So the blue boxes highlighted, those are chosen indexes already. So the index which are chosen, so you cannot use that for the new commands. So the index number 3, the compare, right? So it actually proposed the value, but it is not chosen fully in the cluster.
Yeah, sorry, can we guess why it was not chosen? It looks like S1, S3 has accepted CMP, no? Yeah, we can see the CMP command in S1 log and S3 log, no? Yeah?
Yeah, but the thing is, the same command is not it's not got replicated in S2, right? So when one command got accepted in all the servers, then only we say that command is chosen.
Okay.
If you
So it's
see,
not about majority, yes? It's about all.
okay. The majority is chosen. So okay, let me tell like this. Okay, the value is accepted. That's called majority, and the index is chosen. Then it is chosen across the all servers.
Okay.
So now move and add. I'm sorry. So index 1, 2, and 6 got accepted in all the servers. So the server 1 maintains there is separate indexing saying that what are the index already chosen. So now index 3 is not chosen. For that, now what it does is it picks the index 3 and it's try to put the new command in the index 3, but it sees there's a value is already chosen, CMP. So now what it does is it picks that compare and it try to replicate across all the servers. Now we go to here, the second diagram on the right side. The compare is went to S2. Okay. Now it picks the index number 4 for the client request. We see the flow here, right? If there's a chosen value, then we go to step number 1 and find the log index again. Then you find the log index 4, and there we try to put the new client command, that is subtract, sub. So no, not subtract. There is another command. So now index 4, right? It try to prepare the value. So that is already in that index. Sub is already accepted at the server 2. So now server 1 picks the sub and it try to put in the index number 4 because the value is already accepted, right? So even that index also you can't use for the client command. So now 4 will be sub will be accepted at the 4 also. Now 5 is actually whole. There's no command is accepted here because I said server 3 is down, right? You can assume the server 3 is down at this point of time. So now it picks the index 5. Then it will run the basic Paxos to find out if any value is accepted. Now here it will not find any accepted value, and the index 5 will use for that client request, that is jump command, JMP. So the JMP will be represented 5 at server 1 S2, and then that say accepted, it moves to 7 index. Is it clear?
Can you repeat
So
the diagram once more? Like, I mean, yeah, go ahead, Nick.
yeah, to be honest, it's not clear why GMP not to put at fourth position. Yeah, because there is just one sub and
right. Yeah, that's a good question. So the thing is, so in the basic Paxos, we have told earlier, like for the index 4, in any of the servers, if any value is accepted already, then try to use that value. So in server 2, the sub is already used for index 4. So now it takes from S2 and keeps at 4. So now 4 index is already accepted value sub, right? Then we choose the index 5 for the new commands. And the index 5, we again try to check in the across the cluster, all servers, if any value is accepted. So S1, S2, there's no values accepted for index 5, right? And then, I mean,
CMP is accepted. CMP.
S3, right? S3, I said is down. You can assume that the S3 is down. Only these 2 servers are up, S1, S2.
But how do you know here that sub is accepted? I didn't get that.
I'm sorry?
Like, I mean, how do you get that sub command is accepted?
Because you run the prepare, right? So at that time, the message goes to S2. So he will send what is the last accepted value. It gives sub to server 1. Okay, we'll see the flow here. Let me just go through here.
Yeah,
So
from what I remember, if I think in this prepare phase, if any of the server says no, then it will again try to propose a value, right? That's how it will happen. And then all other servers will say yes to that command sub, right?
Right. So if you see the step number 3, right? Once the server 1 sends this prepare for a particular index, now index 4, right? So then that time the acceptor, he has to acceptor, it gives the accepted proposal and value. So the value here is it already accepted sub. So that gives to the S1. Now S1 will choose the sub instead of his own value, the jump command. Now it will send in accept to the other followers, other acceptors. The same thing happened over here. So in once the S1 sends a prepare to the S2, S2 sends in what is the previously it has accepted the value. It sends it, that keeps its index number 4. Now it goes to the which are free index, right? That index is 5. It checks in 5 if anything is accepted or not. So 5, there's no command is accepted. So that will use for the jump command store. So we need to understand one thing clear here. So now, so here the main advantage of Paxos is it can take values from the any followers, any acceptors. Say maybe it could happen that in the previous iteration, this S2 is the leader. Okay. it got sub, it accepted, but no one else has got accepted. Now this S2 crashed and S1 become leader. Then after that, this S2 came back and it become accepted. So at that time, this scenario will happen, right? Is it clear?
So even if okay, so I mean S1 initially accepted CMP, right? I mean the last command was CMP. Okay, and let's say S1 failed it. I mean after some iteration S1 failed. So next time can again S1 propose any value?
Because once it failed, right? Then we have S2 and S3. Then one of these two nodes become the new leader.
Leader, yeah. So let's say if S1 comes after some time, will it be able to propose any new value or not, or like
no, only leader only can propose the new values.
Okay.
So now in this case, S1 is a leader. That's why he's trying to propose the values.
Yeah.
Okay. If you see the raft, right? So raft, the thing is whoever is the leader, so everybody has to blindly follow that guy. So in case of raft, this sub will be dropped actually. Everybody will blindly follow from the server one. So it will just overwrite actually everybody. From server one, it just overwrites to all S2 and S3. But in case of raft, the beauty of raft is it can take the values, accepted values from the followers as well. So there is no data loss.
But aren't there conflicts?
Where is the conflict you're saying?
I mean, different followers can have different values at that index.
But okay, okay, you're saying, but that will happen. Okay, so if that happens, right? So now the majority. So whoever says the majority of the server says the value is same, that value will be taken, I guess.
Let's say two servers have two different values at index 6. Then which follower will be given the preference by the master?
Two followers.
So for example, S1 at index 6 has RET, right? And let's say S2 has sub at index 6. So which one will be given preference? And here S1 is leader. Okay, we can take another example where two followers S2 and S3 have different values RET and sub at index 6. So what will S1 take as a accepted or chosen value?
If it's a different values, right? You're telling for S1 for index 6 it is RET and S2
No, S1 doesn't have a value. S1 is trying to find a value, and S2 has RET and S3 has SUB, submit. Yeah.
Sub, okay. I'm not sure what happens at that time. So you're saying there's a different, okay, if both are different values, right? Then we could assume that one point of time this S2 as the leader, and then immediately it accepting this the command, it crashed. Then S3 become leader, and then it accepted some new request from the client, and that also crashed, and then S1 become the new leader. So I think the both values will not be accepted, I think, because the client from the client side, we don't respond anything to them because we'll say it's a failure because the majority did not get chosen the value. The client side is clear that the value is not accepted. The client can retry.
Okay.
So at that time, this S1 can propose its own value. It can ignore both, I think. It makes sense, right?
Yeah, sure. Since none of them were actually committed, right?
Yeah, and
yeah,
none of them actually got committed. The client can retry again.
Sure. Thanks.
Okay, if you don't have questions, then we'll go to the next session. Okay, next slide. So here, okay, there's one more thing is the leader can take multiple requests from the client and it can run all concurrently because each index is separate, right, for each client. So it can run multiple, it can serve multiple client requests. And then all the commands has to be applied in the state machine in the log order only. Say now in this case, right? So if you see this one, the S1, it will execute move and add only to the state machine. It will not execute command and RET because it has to go in a sequence fashion. When there are some holes and there's not accepted values, those will not be applied to the state machine. Okay, so for the basic Paxos, right, there are some problems. Say there's multiple concurrent processes, and then all the servers will try to propose their values. So there will be more load. The higher the load, then higher the conflicts, right? So the client request will not be served fast enough. And then we have 2 rounds of RPC, prepare and accept. For every index, we run this, right? For every log index. So that is very inefficient. So for the multi-Paxos, what they did is they picked a leader. At any given time, only one server act as a proposer because the leader will only propose the values. So if you pick a leader, then we can avoid most of the prepare RPCs. And then if you see earlier, right, one index, for every index we send one prepare, but in the multi-Paxos for entire log we can send only one prepare and collect the complete status. So what are the accepted values, and then we are done. And from that point, and then for the new client request, for new request only we can send the prepare, or you can directly send the accept also, because we already prepared, right? So we know that there is no new accepted values. So then at that time we can directly send the accept only. Okay, for the leader election, so for the Lamport, right, what they did is in the Paxos, they didn't give any leader election algorithm, but what he's mentioning is, so this Paxos is a consensus algorithm. So whatever algorithm you choose, so everybody will agree on that. So the leader election is independent of this Paxos, but still we can have like one simple algorithm. Say the highest ID will act as a leader, the server with highest ID. So how it happens is, like, initially all servers will try to send them messages of their IDs, and then everybody will get to know what are the highest ID. So then the highest ID will act as the leader. Say if that highest ID is not responding for the 2t seconds, because every t second they send the heartbeat, and then leader is not responding for a 2t seconds, the t is the heartbeat time, then the immediate highest I mean the second highest server ID will act as a new leader, and that leader will accept the client request, and then it will send the and then here the leader will act as both proposer and then acceptor. And if the server is not the leader, then it will not serve the client request, and then it will say, hey, I'm not the leader and he's the leader, please talk to him, something kind of thing. And it will accept only as a acceptor if it's not a leader.
So leader basically proposes the value, doesn't accepts, right? Is it, I mean, followers accepts, right? You said that leader can also accept.
Yeah, so the leader also will accept, they're saying. So what I understood is, so in multi-Paxos, right? So if there's a split brain, say for suppose there are more than one leader. Okay.
That's
so,
it. But this is a single leader, right? This is not a multi-leader.
Correct. It's a single leader, but the thing is to detect, right, if there's a multi-leader and one can drop. Okay, I mean, I'm thinking that way. What I understood is, like, the multi-Paxos will work even if there's a multi-leader also. But thing is, more conflicts will happen and the client request will be delayed. So
Okay.
to avoid, and then say suppose if it is trying to detect that there's a multi-leader, then while accept phase, I think it detects that there's some leader in the system, the second leader. So one of them will get dropped. I think maybe for that purpose that they are making the leader as accept also, I think. If anybody has an idea, they can give us more. But there's no harm, right? Do you think any functional harm if it's acceptor? But I could see this is the scenario. The acceptor will help.
in multi-leader, you have those problems, right? Split brain and all. So I'm thinking like, will those come into picture here or?
It can happen, right? Say for suppose there is an network partition happened, and then there's a two leaders got elected, and then the problem got solved. I mean, all of a sudden the all cluster become like one network again. Then the two leaders trying to detect they're like one leader, they're a separate leader. So if you don't have accept phase, then they will not be able to find out, right? There is a second leader.
Yeah, then that makes sense.
That's what I'm thinking. For that purpose, I think this acceptor may help.
Sorry, I did not get. Why do you need an acceptor?
Oh, okay. So in system, I mean, this is what my understanding. Say if you have two leaders in the system, okay. So if you don't accept the leadership is not accepting someone the other leader's request, then how it will detect that there is a separate leader exists.
Or separate Paxos will run on two different clusters, right? You had one cluster which have one leader, and after the split build, right? After the partition you told. So it will be divided into two clusters. One cluster will have its own leader, other cluster will have other leader. So now Paxos will be running individually on both the clusters.
Right, but there is a problem, right? Like the partition happened because of some failure, and the failure got solved, and then again they came into one cluster. Okay.
Yeah, but probably we will rely on majority, yeah, and we will have something like time in request, something like epoch.
Correct, but the
Yeah.
majority will help to choose a value. Majority will help choose a value, but the thing is, it will not help to find out if any another master exists, right?
Yeah, but when a host became a leader, he should ask acceptor to be agree on this, yeah, and probably he will wait request from majority of acceptors. So it's not just a leader choice to be a leader. Yes, acceptor should vote for this. No.
I'm not sure. I mean,
I would expect like this. So if I would like to be a leader, I should ask majority of node to be agree on this. Yeah, and probably we will have something like epoch, and if I voted for leader in this epoch, yeah, I will not vote for another leader at same epoch. I will just I can vote for next when someone came with request from next epoch. Yeah.
yeah. I mean, from your discussion, I understood like this accept helpful to win it to conduct a new election. So as they have new election, right? Some new lead, I mean, everybody trying to say for suppose some. I'm thinking this accept will helpful to choose a new leader also, I guess. Say now we have like one leader and then four followers, right? And then say that leader somehow so the leader it got down for some time, and then the second server will try to act as a leader, and then it will broadcast the message, right? And at the time of broadcasting, the leader came back, the previous leader, and it has to accept the message, right, to see there is some election is ongoing. So if master is not act as a acceptor, the leader, then the leader election only the four followers only will follow. The leader will not follow actually the previous leader. Maybe for that purpose we need acceptor. Yeah, does it make sense?
Yeah, it looks good. So you're basically saying the server which was, the leader which was down earlier, right? And all of a sudden it came up, and during that time, the four followers, out of them, whosoever was leader, he was proposing some value. So the master which has come up, he has to accept the value given by what you say.
Right. Yeah, for that purpose, I think it will be helpful acceptor.
Yeah, looks good. Yeah.
Cool. So, okay, if you recollect the prepare phase, so why do you need prepare is to block the old proposals which are not complete yet, and then find out if any chosen value, find out if any chosen value for that index. For these two purposes only we use the prepare. Okay. And then so in multi-pack, so they send one more parameter from the so from the acceptor, right? It can give one more parameter saying there's no more accepted. So in acceptors, if it is not accepted any more values, right? So it can tell there's one parameter, so no more accepted. So for that acceptor, it will not send any more prepares actually. Because as you mentioned earlier, then multi-Paxos, the prepare will be executed only once, right? For the entire log. So for each acceptor, it will try to send the prepare. If any acceptor says there's no more accepted value with me, then the leader, it will not send any prepare request for that server, for that acceptor.
Can you explain with an example?
With an example, sure. Let's just go
You can
back.
annotate. You can annotate here.
Annotate, yeah. I mean, I need to comfortable to annotate, but I have not done. That's okay. We'll just finish this time. Say for suppose this server S2, right? It has move, add, sub, and ret. Say for the time you can assume the sub and ret is not there. They accept only move and add. So when server one comes, will act as a leader the first time, it will send the prepare to S2. Now S2 says I have accepted 1 and 2 index, and then I don't have no more accepted values I have. If these two are not exist, sub and ret. So for that server S2, it will not send the further prepare request for that server S2. So, so indirectly is saying this server 2 is telling, I have, these are the accepted values. Beyond this, I don't have any accepted values.
Okay. So we are reducing the number, like the
number of prepare calls.
Yeah. Okay.
Okay. Say for example, in this example only, say now S2 has move, add, sub, and ret. So when it gives this prepare for move and add, right? So it has still index number 4, it has a sub, right? So at this point of time, it will say no more accepted as false, because still it has valid values, sub and ret. So it can still send the prepare.
Okay.
Got it?
Okay, so if S1 is a leader and it has a value for an index, then that will be written by all the other acceptors, like accepted by them, or they will override their accepted values. So I'm a little not sure about this flow. So let's say S1 is a leader, and on index 3 it was sending CMP. It's sending CMP to all of the acceptors. Right. So now S3 in this example, it has CMP, but let's say it had RET, right? So will S3 overwrite its own value because S1 is the leader and it is telling him it's proposing a value?
Or it will not overwrite like that. We always try to get what is the accepted value based on the majority. So the majority will always win.
Okay, got it. Okay.
Got it, right? Okay, so here until the acceptor says no more accepted, we will send the prepare. So this happens at the only initial stage when the new elector when the new server acted as a leader, the new leader. For initially to get the complete sync with all followers, it will send the prepare. Once after all server says I don't have any accepted values, then it will not send the prepare for that acceptors. And if you get the majority says no more accepted, then there's no need to send the prepare for any of the nodes further. Because when majority means we need only majority, right? Say for suppose one command got accepted only one server. So we don't worry about them because those are already fail commands. The client also knows that those commands got failed. So for those servers, we don't send the prepare anymore.
Yeah, it's like a short circuit. Yeah.
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 Okay, so this point is like only one round of RPC needed per entry. That is accept. Because once prepare is done, then you know what are the accept values. Then now onwards you can send in only accepts. So no more prepare. Then full. So once the okay. So once we get the majority, so we need to still uh, give the data to all the servers, right? That is called the full replication. So the log index is chosen when the majority says yes, but still we need to replicate the whole cluster. So that is a job still pending. We need to take care. And then say one proposer says the entry is chosen, then all servers will eventually will choose that value. And there are like 4 solutions they have provided. Like I mean, there are solutions for each of these problems, how they are doing it. So we'll keep retry accepting until all the acceptors are accepting the new command. And then there's one more. So okay, there's one problem here is like once the master says, I mean the leader says accept the value, only the master knows that the value is accepted. The followers are still having doubt, is this value really accepted or not? So for that, each server maintains a one accepted proposal, one array. This is size equal to log entry. And these entries should be marked as the entry is chosen. So they send the value with infinity. So initially they will mark with the leader ID. So I mentioned like 3.4, 2.5 you seen, right? So those IDs. Once the leader says the value is accepted, means they update the value with infinity. So infinity means no one else can override the value. So this is the max proposal number actually. And then for this index, there is one more indexing that is called first unchosen index. So every server maintains the first unchosen index, saying that say until here the values are accepted, but here onwards I'm not sure. So you need to give the new accepted values. Oh, that I will show an example. Maybe it will be more clear from the example.
Sorry, I did not get if follower can have a gap in his work.
Would you repeat that?
Is it possible that follower has a holes in his log, empty cells?
Yeah, I mean, it could happen, right? Say for suppose in the accepted proposal, it has an array, and then maybe some indexes are like infinity, means already chosen. If you see here, and there could be some indexes he's not sure, because at this point of time someone else is a leader, and that leader got crashed, and the new leader got elected. So it could happen that the old leader, he did not choose this index yet, but prior to that it crashed. Now the leader, the server 3 act as a new leader now, and the server 4. So that problem still happens, right? For that purpose only, we have this accepted proposal array, and then in that it says the first unchosen index. So this all problem happens when leaders are crashing. If the leader is not crashing and it is up and running for many days, then this problem will not happen.
So what does the donate infinity means? I mean, oh, before accept it was infinity, right? Okay. So whenever it takes any value.
No. So initially, right? This contains, say the server 1 is the leader. So that is the sequence number 3, you can assume 3.1. 1 is the server, right? So it fills with 3.1 here. Okay. And then if every server is accepted that value, then leader says that this entry is chosen. then that time they update this entry, they override the entry from 3.1 to infinity, saying if I crash also, if some new leader comes up, they don't have any authority to change this value because they already chosen this value. Nobody else can override infinity, right? Infinity is the maximum value.
So a question about if a new acceptor or like a follower comes up and joins the cluster, then from where will it copy all the values which have already been chosen? Because here are all are infinity.
Yes. So it has to copy from the leader.
Okay, so leader has, okay.
Yeah, because he will be having it. No, the infinity is a valid value.
No, but in infinity doesn't say that it is ret or sub or what, right?
No, okay. Here the infinity is telling that this entry is chosen. This entry is chosen across the cluster. So when you talk to the reader, so he will give all the values. Yeah, that I'll explain. There's one slide for that. So when someone new one comes, and how the values will be forwarded to them. I mean, not the new one. If anyone says that, hey, for this index I don't have any value, then that can talk to the leader. Leader will forward the values until he completely got the values. That follower. I'll explain that. I have a slide for that.
Okay, thank you.
Okay, now in the step 3 of the solution, the proposer tells acceptor about the chosen entries. Okay, so here say the one of the acceptor has index 1A chosen, 2, 3 also chosen, but 4 is not chosen yet. 5 also chosen. So index number 4, the server 5 is the leader, and he has proposed a value. Okay, and then when the log entry moved to index 6, the server 5 got crashed and server 4 became the new leader. Okay, so now so it proposed a value at index number 3.4, index number 6. So when it got a new accept,
what is this? I mean, 4 is the leader, right? I mean,
yes.
4 is the leader. I mean, accepted. I mean, he proposed the value and it was accepted by everyone. What is this 3 denotes? The value proposed by the leader?
So the 2 and 3, right? This should be incremental. So when the leader crashes, when the new leader elects, right, the sequence number has to be incremented. So earlier sequence number the server 5 uses is 2. When server 5 the leader crashed, the server 4 will act as a new leader, right? So it has to increment the sequence number from 2 to 3.
Okay, do you know what is the name of this sequence? Is it epoch or something like this?
They don't use epoch. They just use. I mean, this is like split into time slice only. But the thing is, for one term, I mean, they call term as a one.
Okay, term, yeah.
Leader. So the term they call it is like one time change.
So 4 is the leader, right?
Yes.
And 3 and at 4, 2 is what? I mean, the ID of the leader was 2, right?
Proposal, yeah, proposal
Term.
ID. It's a proposal.
No, it's term ID. Term.
Yeah, this is the term ID. The first number is the term ID for that term. I mean, when the leader is elected, so he will serve as a leader, right? For his term, the 2 is the sequence number. This is a term ID.
Term ID, I didn't get. Can you explain what is term ID? Like how many times it has proposed the value? Is it?
The term ID is if any proposals he makes for that term, he has to use this ID, the 2.
Round number can use it, kind of, right? I mean,
yeah. That's a round number. Earlier slides we have shown, right? That's a round number. And then this leader crashed, and then the new leader came up. Then the term has to be changed, or else people will get confused, right?
So 5 is the value and 2 is the term ID.
No, 2 is the term ID, 5 is the server ID.
Oh, okay. And what is the value that we are trying to propose?
I mean, we don't care about the value because because value is internal, right?
Yeah, probably it's yellow value.
Yeah, because value. So here we track based on the term number and then the master ID. the leader
But
ID.
when you're preparing log, I kind of always imagine this actually log is what action was being taken, right? Like sub, read, all of that we saw. Log should have all those values. What action, what request came in.
Okay. This is an accepted proposal. This is separate indexing. So the values will be present in the log. And this is one more table, the accepted proposals. It maintains how long until what is the value in the log got accepted. Okay, is that clear? Okay, so now assume at this time the server 4 is the leader with the term number 3. So it proposed a value here, and then the same server sent a accept with the new proposal. So the proposal, the term will be same, everything. The new index is 8. The value is v. For the index 8, the new proposal will get updated, and it says first unchosen index is 7. So until 7, everything is chosen. Okay. So what it says is like now the which are smaller than this unchosen index 7, right? So now 6 is smaller and it is equal to the same term, the same from the same master, the leader. So those will set this to infinity. So this is algorithm for that. I mean the steps they whatever using. So I mean it's clear, right? They're telling the first unchosen index is 7. So until 7, everything is chosen. So now all the acceptors which is matching the same term, they will mark those indexes as accepted. Integers are chosen. That's why we put index 6 as infinity. But this index 4 will not set infinity because this value is proposed by the previous leader. So this guy has to separately talk to the leader, the new leader, and get the value for this index 4.
So why at 8th index we have 3.4? I didn't get that. Like, I mean, until 7.
Okay, that's a good question. Say now index 7 is I mean you're saying instead of 8 they could have choose index 7, right?
Yeah. Because up to 7 everything is accepted, like by all the nodes.
Yeah, because the client the leader can serve the client requests parallelly, right? Say it already sending one some other client request over here, but this acceptor got the index 8 first, then index 7.
Come again, I couldn't follow the statement.
Okay, so the leader got 2 requests. You can assume 2 client requests. The client request 1 uses index 7. The client request 2 uses index 8. But this acceptor got the second client request.
Okay, the 7th
got earlier than the first client request.
First, right. So,
okay. Sorry, I do not understand why logs are not same. Why? As example, cell 6. It's not the same button and yeah, at first row and at second. I would expect same log, same value in each vertical line.
No, would you repeat that where it is not same?
Oh, here, yeah. Where is your cursor? Yeah, it's not the same if we can compare to the apps. No.
I'm not getting your question. Could you repeat that?
Yeah. Is it correct that logs should be the same? So we have 2 rows. Yes, the first row and the second row.
Oh,
They
no,
are.
this is not. So these both rows are same only. This is prior to accept and this is after accept. How this?
Okay.
Both are same. This is like we send an accept request. The prior to that, what is the state, and after accept, how we change the state, how the state got changed. That we are trying to show here. So
nodes, it's just one node, not the log, yeah.
Yeah,
before
this is
and after.
Same acceptor. Okay. Cool. Okay. This is one tricky actually. So say for suppose the previous old leaders, right? It might be having some extra indexes, some extra values. We have seen earlier example one diagram I've shown. leader will not have those entries, but some of the acceptor has it. So those might be the old leaders. So then that time when accept so those old leaders now they act as acceptors. If they send the first unchosen index and acceptor replies, then the leader checks if it is greater than his own unchosen index. So it is smaller than his own unchosen index, then that time it will propose the success RPC. I mean, it as a whole, I mean to say. The leader has first unchosen index is greater than the followers. Then that time it has to send the new request, right? Whatever is the follower is not doesn't have values, those will be sent in success RPC. So in success RPC we send index and value. So now the follower, the acceptor, in the acceptor value they update the value v in the index, and then the accepted proposal they say infinity. So now at this time we directly make it infinity, because in success RPC sends from the leader, it says the index is already accepted it, then we directly set as a infinity. And then the old leader now acceptor, they send the first unchosen index again, and then this loop continues until it gets all the values. There's one question here: what if it is smaller than this? Then we don't do anything, because that value we still need it. Once we go to that particular index, we take the value from that. Let's say the example of here. See this one, we don't override this sub. We still need the value, so we don't do any action until we go to this index. Is clear?
So this okay, first unchosen index is decided for the next what is it, next round, right?
Yes. Another round. I mean, we are trying to sync the values between the leader and then the followers. And what he's trying to say is some of the old leaders, now the followers, right? They might be a valid values in the later indexes. So we don't want to override them, right? That's why we put this condition.
The proposers first unchosen index. Proposers and success. Which is greater than first chosen index. Okay.
Okay, now they're explained from the client side. Any question? Okay. So now when the new commands comes from the client, it goes to the leader. The leader is unknown, then the client can connect to any server. And if that particular server is not the leader, it will just redirect to the actual leader. So here the leader, it has to be the new command has to apply to the state machine fully. Then only it will send the proper response to the client. So if request times out, say leader crashes, right? Say for suppose the client issues the command and then leader has sent to all the acceptors, but prior to sending the response to the client, it crashed. So that example is here. So if it crashed, right, then the client will not know about what is the status of that command. But the master has applied the command in all the servers. But the client did not get the acceptance act. So what it does is now client can try again, right? Second time. When the client is trying second time, what if that applies again? Then there's a duplicate entry in the state machine, right? So what it does is there's a solution, they have found it. So every client is assigned with a unique ID. So whenever they give a new command, the state machine checks internally if that command is already applied or not. So if the command is applied already, then it will not apply the second time again. We ignore the new command, and the previous status it updates to the client. So from this way we can get exactly once. The command will be executed only once. by storing the client ID. So, but the client crashes, right? Then we are not sure what is the. I think the client ID they have to internally cache it. If they don't cache the client ID, then we are not sure what will happen. And then what if the configuration changes? Say, so for every server will be having an ID and an address. And then the configuration would be like we replace the failed machines and change of the degree of replication. Say degree of replication means like now the cluster size is 3. Now we are trying to change the cluster size to 5. So how do you make the changes? So in this case, right, say initially we have 3 nodes in the cluster, and now we have added 2 more. Now total the new configuration is 5, old configuration is 3. So the configuration change is not taking effect properly. Then it could happen that one command will be chosen old configuration, and the new command can take the second command can be taken by the new configuration. So in this way, the consensus will not be clear. Okay. Say here the value v1 we chosen with old configuration means the majority 2, and the v2 command took the new configuration, and then it got reflected in the 3 of the nodes majority. So for the same index, for the same index, so 2 servers accepted v1, and then the 3 more servers accepted v2. So this is not a feasible solution, right? If we do that, then we might be having a data loss for the command v1. So how we are solving this problem is, so to manage the configuration, what they do is this configuration also they make it as a log entry. So they replicate the log entry across the servers, same as like what are the client commands. So it'll treat as a client command the configuration. It stores as one of the log entry, and it replicated across the servers. And they say like this alpha I minus alpha. So once the new configuration got stored in the log entry, that will be applied based on this alpha value. Say we have a 3, right? Say we are here at index number 4. So index number 4 minus 3, like index number 1. So at index number 1, if you have a new configuration called C1, that take effects after alpha value from 4 onwards. And then 4, 5 uses C1. And then again, we have a new configuration index number 3. This will take effect after, plus 3, alpha is 3, right? Plus 3, it affects from 6 onwards. So in this way, the whole cluster will be in sync with the configuration. The whatever problem I have mentioned earlier, that problem may not happen with this approach.
So how do you choose alpha here? Like
that is a concurrency level, they said. I mean to say, okay, the intention is, so at index 4, I said, right, 3. So they know that to execute 3 commands concurrently, they know that the first command will get executed, will get stored in all the followers, all the acceptors. Okay. I mean, based on the so how fast are the servers, the stability of the acceptors, based on that they define this alpha value. I mean, they're giving a one window time. So the window of this alpha, they make sure that the starting command of that window will get accepted across all the acceptors. That's what they want to say. Okay. Yeah, that's all. Like we have like basic Paxos. We have two phases: prepare and accept. For multi Paxos, we need to choose the log entries. Then we need to so in the basic Paxos we don't choose any log entry because we try to do it for only one index, right? For multi Paxos we have a complete log entries. We need to choose one index for one command, for client command, and then we need to elect the leader, and we eliminate the most of the prepares. Only one prepare we use it. And then full information we need to propagate to all the acceptors. Then we talk about client protocol, how we are done, say client crashing or the leader crashing, how we take care of avoiding duplicate commands by using a client ID. And then the configuration changes. So here the degree of number of nodes, if it changes, how we do the consensus among all. Yeah, any questions? I think this is the last slide.
Yeah, could you please clarify if we can achieve strong consistency with basic Paxos?
I mean, the basic Paxos, okay, strong consistency.
Yeah, linearizability or strong consistency.
Yeah, so it has a strong, okay, let me, maybe the previous one, if we show here, this is the basic Paxos, the flow. What we do here is, so first, while trying to propose a new value, we always has to make sure if any value is already accepted in the system, at least one of the node. So we talk to majority of the nodes. So in the majority of the node, if one of the value is already chosen, so that value we take it. So we will not override that value. And then that we send in the accept mode, in the accept RPC. So that goes to all the acceptors. And then that value will be propagated across all the servers. So in this flow, right, it is guaranteed that the accepted value will not be overwritten.
But it will be accepted by majority of nodes, right? So it's consistent. I mean, strongly consistent. No,
Yeah.
more than half plus one of the nodes, this value will be accepted. Then only it will be considered as like proposed. I mean, what do you say? Accepted value, right? So don't you think it? I mean, you get kind of acknowledgement from all the followers that this value has been accepted.
But there
Isn't
is
it
one more trick here. So the accepted value is not accepted in the majority, but the thing is, we spoke to majority of the nodes. Say we have 5 nodes, right? So when you say majority means if any value is accepted means that value should be propagated in the majority of the nodes, right? So that there's a overlap. So if you take majority, the overlapping, you will get the majority value always if it is accepted. And that value we are trying to propagate for the future accepts for that index. So in this way, the consistency is strong.
that is what I'm saying. That
Yeah.
I mean that implies strong consistency.
Yes. Yeah.
Yeah, but it's this algorithm is not that straightforward, especially in the multi-Paxos part, right?
Yes. I mean, yeah, it took so much time to understand this complete flow.
Exactly. It
It's
will
not
take
easy.
true.
And then I want to tell you one thing: this Paxos is the most complex one. They say so because of that. This Diego Ongaro and then John, they are like Stanford University. This guy is a PhD student, and he tried to explain this Paxos algorithm to John, and he's not happy. He didn't convince whenever he's trying to explain because somewhere around they found some problem. I mean, so the algorithm works well, but we are not able to understand clearly. One should go to off the flow. So then they implemented a new algorithm called Raft, so that they made simpler. So
Okay. Base is Paxos of Raft, right? I mean, Paxos they simplified. Raft is a simplification of Paxos. That is what you're saying.
right.